So, after such a good introduction, I have nothing else to say, actually. I'm Julien Van Egg. I'm French, but I work in Brazil. And I'm going to present you static binary analysis, especially how you can make it really easy with a domain-specific language. So, just like a couple of words of introduction. Static binary analysis. So, you guys probably know what is binary analysis. So when you have malwares and stuff like that vary in everything you can have in binary code. Am I speaking too fast? Okay. So, binary analysis, you have the binary code, so source code, you compile binary code, and static analysis. So what is static analysis is analyzing the code without execution. So basically the point is we have binaries, we take them, we analyze them, and we deduce information without execution. That's what is static binary analysis. Domain-specific language, well, when it comes about a programming language, you have a general purpose language, like the C language, C++ language, Python, this kind of language. And you have domain-specific languages, which are languages you cannot do everything with, but it's like built toward a specific problem. And in our case, the domain-specific language of the RSE framework is toward static binary analysis. So it means that the constructs of the language are especially crafted to analyze binary code. We're going to have a focus on vulnerability analysis. So we're going to show, for example, how to detect double freeze, how to detect memory leaks, how to detect simple heap corruptions. Honestly, well, this topic about static analysis is very actively researched in the academy, and there is very few work from the hacker community yet. Well, a couple of people. But I'm going to introduce what is possible to do, and it's not in any way everything which is possible to do, or even it's not like a perfect analysis. Oh, you're going to understand when I'm passing a couple of slides. Okay, let's start it. So I'm going to start a little bit by an overview. What is static analysis? What kind of properties we want to verify on binary code? So just a little word about type state properties. And the techniques we use to deduce that information. So two main techniques in that work. The first technique is called program transformation. I'm going to explain what it is. And flow analysis. So flow analysis, you have control flow analysis and data flow analysis. The two will be covered. A little bit of practice. What are useful program transformations? Showing the results, small demo, and how you can implement it in the domain-specific language. Okay, so let's start by the overview. So as I said, static analysis is determining dynamic properties, which means execution properties, but without execution. So basically what we want to do is to take the binary and to analyze it. What are the properties of it at the execution level, but without execution. So we have different kind of properties. Some can be related to control flow analysis or data flow analysis. Usually static analysis is done at the source level. However, on that work we have focused on binary level. It's much harder to do static analysis on the binary level because there are so many information we don't have anymore. For example, the types. Each variables have type, and in the binary code, the types are not here anymore. So we cannot rely on type information, for example. What is type state checking? So everyone knows what is a type, right? So you have the integer type, well, long, short, etc. And the type of a variable does not change through the execution of the program. The variables have a unique type for the whole program. However, they can have a different state. For example, you have a file, the file can be opened, can be closed. but the file descriptor is still the same type all along the program. However, the state of such a file descriptor is different. It's like an open file, a closed file. Okay, this is a type state. So it's a little evolution of the notion of a type to include those properties of variables that change over the execution. So for example, I took the example of file descriptors. You can take the example of memory chunks. So when you do a malloc, the chunk is allocked. When you do a free, the chunk is freed. It's going to be a bit clear. Oh, the kind of property you can automatically detect is a file closed correctly, or can either a path of the program where the file can be closed twice. Well, for those of you who've been doing a bit of exploitation, you know that a double close is exploitable. Well, it depends on the operating system. But for example, if I remember well, Saint Mail a couple of years ago, with an exploit written by LSGPL was based on a double close. Or double free. Nowadays, you cannot exploit double frees in Linux, for example, because there are additional checks. But it's not the case of all operating systems. So these kind of properties are called type state properties because we can actually define them with a finite state automaton. So small automaton, so you have states and transitions. So these are the correct transitions for a buffer. You can allocate it, you can disallocate it. If you are in the first state and you allocate the buffer, you switch to the second stage. If you unallocate it, then you come back on the first stage because then the buffer is just not initialized. You can use the buffer while you're there, and actually just forget about that part because it's not really useful for our purpose. Well, the point is that the property, the correct state of a buffer can be represented by a finite state automaton. This is the main point of type state properties because all kind of type state properties can be represented by finite state automaton. And this is going to be useful for us. Any question about that? Oops. Any question about this, or is it very clear? That's all fine? All right. Okay, a small introduction about program transformation. So basically, when you want to analyze a program, especially binary code, which is totally unstructured, you want to recover the structure of the program. So by default, a binary code is just like a sequence of instruction. But then you can start to structure the program. You can start to compute its control flow. So you compute the control flow graph. You can start to compute his data flow. Well, each variable actually has its own data flow. And variables can depend on each other. So in that case, data flow are merging. But also, especially again at the binary code level, you can want to transform the ASM, the assembler, into intermediate form so that all the remaining analysis is done on the intermediate form. So that you just have a small backend to translate, say, Intel to intermediate form, Intel code to intermediate form, Spark code to intermediate form, MIPS code to intermediate form, any kind of architecture. And then everything else works on the intermediate form. So you can do control flow analysis, data flow analysis on the intermediate form, which means that the analysis is not dependent on the architecture. And this is very important for binary level analysis, because you don't want to rewrite an analyzer for each architecture. So the first point about binary analysis with program transformation is to transform the assembly code into a more abstract version, which is an intermediate representation that allows you to do a generic static analyzer for whatever architecture you want. Well, you have different techniques to implement program transformation. The first technique, well, the most known technique is actually in C++ using a design pattern, which is called the visitor design pattern. So, well, I'm not going to talk a lot in details about that, but there is a very good book about design patterns in C++, which is called Design Patterns. If you guys don't have it, or you guys are C++ programmers, you should. It's a must. So So I'm not going to talk too much about it because it's too much of an implementation details, I would say. I just wanted to mention it so that you guys can look it up later. All right, just also, this is like a meaningless slide. Don't try to find anything inside that. I just wanted to show, for those of you who don't program in assembly, what is assembly. So just a couple of instructions on the Spark architecture. So you have instruction for writing in memory, instruction for performing arithmetic operations, like add, sub, mul, like multiply, add, etc. You have instruction to read the memory. You can have a bit level instruction, for example, XOR, which is a... Can someone remember me what is XOR? It's an exclusive OR, thank you. Well, nothing, or comparison instruction, etc. So we have in our framework called RSE, we have a full support for this architecture, and we have almost full support for the Intel architecture. So Intel architecture has around like 350 instructions. So it's quite difficult to have a totally complete backend for the Intel architecture, but we're working on it so that we can improve. Okay, what is control flow analysis? So basically, when you have a small code, for example, if you have a if-else, then you have a conditional code where you're going to find these kind of patterns. So basically, for example, if you have a if, you can enter here. If you have an else, you can, well, let's put it like this way. If you have an if, you can enter here. If you have an else, you can go here. Or you can do loops as well. So this is a control flow graph. It means that the structure, the global structure of the program can be analyzed in such a way. Instead of like having a sequence of instruction, you can do a first structuring using control flow analysis. Well, sliding and sliding, I'm not going to explain too much either because it's not the point of the presentation. I just wanted to introduce what is control flow graph. It's really nothing very complex. I'm going to especially focus here on data flow analysis, and here I'm going to enter into details. Sorry. Honestly, just with control flow analysis, you cannot do a lot of things. You just can, well, a couple of properties like safety properties or liveness properties, which means you never pass through a certain state, or you can always pass like an infinite amount of time through a state to make sure you don't have a deadlock, for example. So this is a liveness property saying you don't have a deadlock. Or safety property, which we, for example, a buffer overflow, when you say that you don't want to enter into a state. So the two main kind of properties that you can apply to control over the control flow graph, that you can verify on the control flow graph, are safety properties and liveness properties. However, most of the interesting properties needs to be done on data flow and not control flow. That's why I'm not going to extend very much my presentation about control flow. Okay, this is much more interesting. So this is a kind of data flow graph. So I have to say each node here is, for example, a variable or a register. Here in green you have malloc, and in red you have free. So the output of malloc, or malloc, as you know, return a pointer, and on a pointer on the allocated region of memory. So here what we do after our control flow analysis is a data flow analysis that allows us to understand the dependencies between the variables. So already, I think you start to understand what kind of properties you can detect with that. So if green is malloc and red is free, or you can detect at least two kind of problems here. Can someone tell me? Sorry.
A memory leak down there, the blue dot on the left.
Which node?
The last one on the left of the red one.
That's right. This node. So for example, here you have a data flow path where it starts by a malloc and then it doesn't finish by a free. So if you malloc a buffer and then you have a data flow that ends up without being freed, it means that you have potentially a path of the program where the variable is never freed. So this is the kind of property you can detect. For exploits, it's quite useful to have memory leaks generally because you can do heap spraying and stuff. So if for you, those of you guys who were at Bacon, you heard a little bit about the heap spraying. Heap spraying is when you configure the heap so that you can predict exactly where the address is, for example, where your shellcode is located. So that it allows you to do very efficient exploits. So memory leak vulnerabilities, or it's not really vulnerabilities, but well, the fact that you have memory leaks is definitely useful for writing exploits. You have another potential problem here. What it is? Any idea? Not a single idea. Idea.
Something with node 28. I'm not sure.
Well, here on node 28, you can actually think that it's also a memory leak because it's a malloc that doesn't end up by a free. But it's not my point. My point is that you have two paths that goes from a same malloc to a free. So the same variable is actually potentially freed twice. You can actually, a single malloc variable can be freed twice because it has two data flow paths leading to a free. And this is another type state vulnerability because you free twice the same variable. So this is the kind of analysis that we're going to talk about here.
What does the arrows mean and the blue things mean?
The blue is like a, do you know a bit about data flow analysis, or should I explain def use chains and stuff? But well, basically, just to answer quickly, the blue stuff, the small blue nodes are intermediates in the data flow. For example, if you have a variable that stands in memory, if you write it into a register, and then this register is reading in memory, so the very first, you have at least three def use, which means that here you have the malloc, then the pointer of malloc is used, or it can be put in a register, and then it can be put in another register. Well, you have operations of the program using the pointer. So this is what represents the intermediate node, what is represented by the intermediate nodes. So each node is actually a use of the variable. Is it clear, or okay? And the big nodes are just the extremities. It has no special meaning, it's just that it's the extremities. Okay, so now that we have introduced quickly the data flow analysis, I want to talk a little bit again about program transformation. So usually we have a hierarchy of transformation. You don't do a single transformation. Earlier on, I talked about translating assembler code into intermediate representation code. But usually you do a first translation to a very basic intermediate representation. And later on, you can take this intermediate representation, and then you can translate it again to another intermediate representation, which is suitable for a particular kind of problem. So the idea is to dilute the complexity of the analysis into the intermediate form, so that you don't have to write very complex algorithm for detecting vulnerabilities. You just need to find what is the best intermediate form for a particular property. So in our case, so we have first the architecture backend, so the one responsible for taking the assembly code and making a very low-level intermediate representation. Gate visitor, well, forget about the name, it's not a standard name, it's just how it is in my code. So gate visitor is to propagate data flow analysis, data flow information to other procedures. So for example, when you pass a variable as a parameter, then you have a data flow link that is flowing through another procedure. So this is the role of a gate visitor to do those associations. Alias visitor, this is very interesting because it's one of the main problems of static analysis. You can have variables which have multiple names. For example, if you do character star ptr equal malloc, so you have a variable which is named ptr, which is a malloc, and then you do ptr2 equal ptr. So it means that you have two variables which are ptr and ptr2 that points actually on the same buffer. But because of that, you might miss bugs because you don't know that the two variables are the same. Obviously, I'm just giving you a very simplistic example, but you can have very complex alias analysis. For example, you can construct address in runtime. You can have arrays of an index, and the index comes from the network, for example, or something like that. So in that case, you don't know exactly if one variable has just one name, or if you have a pointer that point in the middle of an array. So you have potentially multiple names for the same variable. So the alias visitor is actually resolving these kind of problems. You have mainly two kind of alias analysis. Well, actually just one, but one is a subset of it. The other one is a subset of it. One is called set-based analysis, which means if you have variable A and variable B, so if variable B has a set of potential aliases, then if you do A equal B, then you say that A has the same set of potential aliases. So basically, if B can point on two different variables, so A will point on two different variables. And you have a small refinement of that analysis, which is called subset-based analysis. So basically, instead of saying that those two variables A and B have the same sets of aliases, you're going to say that B has a subset of the alias of A, which is slightly more refining. I'm not going to talk forever about alias analysis. It's a huge problem. You have like hundreds and thousands of publications on the internet about that. If you're interested, just look it up again. The presentation is not aiming to go very in depth into a specific topic, but more like giving you a general introduction to it. And the heap visitor, though. So the heap visitor is once you have constructed the data flow graphs, and once you have resolved actually the most obvious aliases, then the heap visitor is just a depth first search, like a DFS algorithm. So just passing the graph and seeing if you have passes that are potentially vulnerable. So in that case, it's 4 malloc and 3 buffers. Of course, if you want to analyze like double close, well, it's the same algorithm, but it's not really a good name, heap visitor. Anyway, that's not the point. So this is just a bullshit slide. All right, about the alias analysis, because it's really, really interesting. For example, it might be, so again, this is a malloc, and the red one is a free. So it might be that you have multiple aliases, and actually this variable is the same as this variable. But you don't know because your alias analysis is not powerful enough. So you actually end up with those data flow graphs, which are the same graph that I just presented a couple of slides ago, just that, well, if you check out the slides offline, there is a name of the variable inside. So those are registers, the blue ones are registers, and the orange ones are memory accesses. So this is a typical problem of aliasing, because you might think that there is a missing free after the malloc, but actually there isn't, because you're not capable to associate the two aliases. So this is a kind of problem that has to be resolved generally in a conservative way, which means it's better to say that you have more aliases than not to have, because it's better to have false positives than false negatives. Any question about that? It's all clear. Okay, good. Yeah?
That's why you say that you make a set
That's it. So you can actually connect the two data flows, because you have
You don't have a strong connection at that point. You have a possibility that's
exactly. So this, well, look up a little bit of alias analysis on scholar.google.com. I think you're going to enjoy it. There are so many techniques about alias analysis. I just mentioned the main ones. Oh, by the way, I need to tell you before I forget. I'm sorry for not talking this morning, because I was supposed to talk at 11:30. However, we had a party until 6 o'clock, and blame the bacon organizers because they paid us free beer. Okay, so the heap visitor that I mentioned a little bit already. So usually when you want to know, for example, if you are missing a free, you start by the malloc and then you follow the data flow, and if you don't reach a free, then you have a missing free. So it's a forward analysis. On the other side, if you want to check, for example, if you are freeing a variable which was not mallocked, then so you start from the free, and then you see the ancestors, and you see if you reach a certain point, for example, a stack variable. So it means that you might have freed a stack variable, which obviously is wrong. So it's two complementary approaches. The forward analysis, for example, to detect memory leaks. If you want to detect like free of non-allocated buffers, then backward analysis is more adapted. Okay, some results. So here, detection of multiple dislocation of memory leaks and heap corruptions. So I'm taking C code, and it's totally stupid code. Totally stupid. It's just for everyone to understand. Obviously, it works. This technique works for larger and larger code, not like 5 lines of like a dummy C programmer. But it's just for everyone to understand what we are talking about. So here you have a totally obvious double free. Why? Because you have a function called TT, which is freeing its parameter. And just after the TT function, you have a free on the same. So you have a double free, which is totally obvious, and no one should ever do that. And probably no one has ever done such a stupid program. But it's just to explain and to show what it gives on the data flow. So here, for example, it shows that we are capable to reason interprocedurally. It means passing through the procedures, because we're capable to resolve that PTR and A are the same variable. So here, what it gives, you have this. This is a data flow graph. So you have malloc, it passes through certain registers. Then it writes into memory, because you have the parameter passing, so it's passed on the stack. And then it continues until it's freed. And on the other side, you also have another freed, because you have two paths of the program which are freeing the variable. So this is what it gives, and this is the output of my program. So it gives you exactly the addresses where the data flow where the data flow is not computed, but where you find the definition of the variable and the use of the variable. So here is the address of the instruction. This is just an ID, an identifier. Okay. Nope. I'm off. Am I off? So this is just the address of the instruction, the identifier for the instruction, because I give a unique identifier to all nodes, like abstract nodes, which can be instruction, operands, or whatever. So I'm capable to look up a given node during my static analysis, uniquely using its ID. And this is a very simple intermediate form. It's almost not an intermediate form. It's just a pretty printing. But well, the main point is that we have that in param I0, which is the output of malloc. So in my case, I have like a special type, which is alloc, and a special type, which is free. So the graph, my data flow graph, is actually a graph of typed nodes. Each node has its own type, and so you have the alloc type, the free type, or whatever. And you can use the type information. This is the main point of the visitor design pattern. You can use the type information, and depending on the type information, you can do a different analysis. So in C, you would do like switch. You would have a field of a structure saying point type equal something, like the type of this node is alloc, the type of this node is a register, the type of this node is a free, etc. But then, who codes in C nowadays, you mean? I mean, C was good for the 70s or maybe for the 60s, but well, to write a static analyzer is definitely not a good language. It's not adapted at all. So that's why C++ is already an improvement. But C++ has lots of limitations. That's why we don't use C++ anymore in our project. So here, an example of double freeze. So it gives you exactly the path of data flow for the two frees. Other example, so in that case, we have a missing free, like it just returns 0. Again, totally stupid example, just to make the point. So you can find actually passes that are without free. So in our case here, this pass is without a free. We have a malloc here, and we have one case where it's no free. Again. So here we actually have found two vulnerabilities. One was a double free, and the missing free is, well, obviously it's not ending by a free because it's a missing free. So it starts by an alloc, and it finishes without a free. Totally stupid program, just to make the point. You free something which is not a buffer. So we put 3, a constant 3 into A, and then we free it. That gives this. So here you have a malloc, but it's not the point. And here you have the free, and you can see that the ancestor of the free is an immediate of 3. So this kind of stuff you can detect, basic heap corruptions. This approach works very well, not just for A equals 3, free A, obviously. It works for if you have a free of a stack variable, it will detect it without a problem. Unless you have a hard problem like alias analysis and you're not capable to associate and stuff. And well, it's not the point either to talk forever about alias analysis. And again, it says that there is a missing free and also a free of unallocated variable. All right. About the code. So this talk is entitled Static Binary Analysis with a Domain-Specific Language. So in the RSC framework, we have developed a domain-specific language for static analysis, which means that we have a very, very handy language to write static analysis. So it's usually for prototyping because a domain-specific language, well, our language is interpreted, it's not compiled. So it's slower than if you write everything in C, for example. But it's just to make some prototypes to see if such or such analysis is working correctly, if it's working, if it's valuable, if it brings result. And it's just like a preliminary stage of development to see if actually an analysis is valuable. And then if it works, then you can eventually optimize it by implementing it into another language, or why not writing a compiler for the domain-specific language, but it's a lot of work. Oops. So for example, in our domain-specific language, we can declare types. So I have to say that the syntax of that language, the syntax is quite near Python. It's not like Python, but it's the nearest thing I can think of. And the semantics is like ML. So meta language, like anyone programs in ML? Objective Camel or Camel? No one? That's too bad for you. Well, ML is like an awesome language. It's honestly, I think, the best programming language ever. Because you can basically switch, not only switch on the value of variables, but also switch on the types of the variable in runtime. So you can do lots of powerful analysis just based on types. Anyway, so the syntax for type declaration in our domain-specific language is like that. So we can declare like a complex structure, even recursive structure, mutually recursive structure. This kind of stuff is not a problem. Here, for example, we declare a type for representing what is an operand and what is an instruction. So in our language, well, it's just a little trick, but this stuff here with a percent is when you don't care about the type. You don't know exactly what it is, but you say it's such size. So you are capable to say, okay, I have a structure. I know more or less its type, but there is pieces of the structure that I don't know what it is. So it's useful for reverse engineering usually, because you say, okay, this part of the memory, I don't know what it is, so I put a percent and the size of this memory, and so I'm capable to describe a global type without having to declare every single type fields. So in our case here, well, we have a disassembler which is written in C, and there is an internal structure which is pointed by the proc field here. But we don't want to mess with it at the level of the domain-specific language. So in our case, we just do %4 to say it's a pointer, but we don't care about it. So don't be bothered about that. It's not really important. Oh, it has evaluated since I made that presentation actually. We have more than, some architecture can have more than 3 operands, so you need more than 3 operands. Or you can do arrays here. And I think some architectures have actually up to 6 operands. So 6 potential parameters to a single instruction. So the same thing, how you declare structures. What is pretty cool is that I think you can do it in Python as well. If you declare a structure type, then you don't have to initialize all its fields. You can just initialize the fields that you want. So our language is capable to do that in a syntax which is very, very dense. And obviously you can initialize subfields with other structures and stuff. So this is how we're going to declare types. How we do to, or you remember when I talked about control flow analysis. So in just a couple of lines, a bit like Python too, you can parse the control flow graph. So you can visit the children of each node in the control flow graph. So just by doing a for each and then calling the analysis function over the next box, you have, in that language, you have hash tables. So, for example, here you have a hash table that associates to an address a 1 or 0 to say if it was already visited or not, so that you don't loop forever on the control flow graph. This is how you can work on the control flow graph here. Okay, this is the main point of the domain-specific language. This is why the language was done. Everything I presented in a couple of past slides is just standard. You can do the same in Python and probably better. But this is the point. This is the point that is going to help us to do program transformation. We have a construct which is called rewrite and end rewrite. So it's a pity that you don't program in ML, because I would have done an analogy with match in ML, but it's okay, I can explain without that. Basically, what we do is we do a case, and not on the value of a variable, but on the type of the variable. So that actually, once we have disassembled a program block per block, and then we have translated it, well actually we want to translate it into an intermediate form. So depending on each type and value within the structure of that have provided the disassembler, we can do a transformation. So we have many syntax. I'm going to illustrate this with an example just to give you the syntax for now. So if you have a certain type in input, you can say you want to transform into another type. Or if you have a type, you can say you want to transform it into a list of types. So for example, if you have an instruction, for example, on the Intel architecture, and you want to translate it into multiple intermediate form instruction, so you need this construct. For example, a push is going to be writing in memory and then decrementing the stack pointer. So you have multiple operations in a single instruction, and then you will need this kind of construct 1 to n. Also, for when you transform instruction, you can execute commands and before and after transforming. So that allows you to do side effect to the transformation. A bit later, we're going to explain how we use the pre and post commands to compute the data flow for each instruction transform instruction. So 1 to 1, 1 to n, 1 to 1 with pre or post or both. Also, you can also do this syntax, which is which is a summa basically of this, but on single line. So if you have source type 5, you translate into this destination type 1, and then you execute post command just with a question mark like that. So it's the same than this, except you don't have the pre. It's this in a single line. Or rewrite n by n rewrite. Or you have also a default statement, so that if you, for example, if you don't support an instruction, then you can say, okay, I don't support this instruction. So allows you to debug the static analyzer. This is the attributes we give to instructions. How we do to know how we have to translate the instructions binary code into high-level instruction or high-level operation is that we give attributes within the disassembler. We give attributes to each instruction. So we have attributes to say that this instruction is calling a procedure, or is doing an imperative branch, conditional branch, is returning from procedure, is doing an arithmetic operation, is testing a bit, is setting a bit, is calling an interruption, is reading into memory, or writing into memory, is doing assignation, comparison, it's using a status flags, or writing a status flags, or it's a prologue, epilogue, or even it stops the machine, or it does nothing. So those are the main attributes we give to instructions. So this is just a matter of naming. Basically, we have all those attributes I just said, and to make sure we can manipulate it easily, so we define them with short names. So the imperative branch attribute becomes B, conditional branch becomes CB, calling becomes C, etc. So this is just to have short names so we can manipulate them more easily. And those are how we define the very first intermediate representation, low-level intermediate representation instructions. So those are the highest levels, so those I guess you can understand pretty easily. Like ternary operation is when you have two operands and result in a third operand. Or if you just have two operands, then you can still represent it as a ternary operation, because it takes two arguments and write into the second argument, so it's like A equal A plus B or stuff like that. Like a ternary operation involving 3 registers, ternary operation involving a register, an immediate, assignment from an immediate value to a register, from an immediate value to memory, from register to register, from register to memory, from memory to registers, comparisons, bit set, bit test, etc. And the point of that intermediate representation is that it's independent of the architecture. So once you have translated the program into such intermediate presentation, everything else after is independent of the architecture. So it has no special meaning to just do that, just translate into an intermediate representation. The point is that everything you do after that is independent of the architecture. This is how we define them in the domain-specific language. So just still using type. The double dot here is subtyping. So, but it's like inheritance. However, it's just about structures, though. So it's record subtyping. And so each register has an ID. Each immediate value is stored in a long. And basically, this is also all code, because since that time we have modified the mem so that it is capable to handle construction with a scale, for example, well, Intel instructions basically. So here in that abstract description of an operand, you might have more fields. Well, you just have to add a field like that, and that's it. So this is how you do it in practice. So this is a comment actually. There should be a dash here, but it was like eaten by LaTeX. So this is a comment in these two. So basically, thanks to our instruction attributes, we can deal with multiple instructions at the same time. So all those we know that it's reading memory. So the instruction is actually an assignment that is reading memory. So the flag RM, remember, it means read in memory. And all those, as soon as it has this flag, then we know already that we can transform it into async MR with the good fields, and the field that comes from the instruction here. So what we do globally is we do a for each instruction of the instruction list of the block at QADDR. As you see here, we initialize QADDR with the address of the current block analyzed. So this function is called by the small function that parse the control flow graph. So the control flow graph is going to call this transforming function for each basic block, so that actually each instruction of the basic block is translated in this way. Any question about that? You can probably do it in other languages, or in ML you can do it. However, the syntax of ML doesn't allow to do everything we do. So we have simplified a little bit the match construct of ML to make the rewrite construct, and the syntax is a bit more smoother. Is it all clear? So I just gave two examples because obviously the backend for the architecture is huge. It has like more than one, oh, let me think. Well, for Spark it has a couple of dozens of Ks. I'm not sure if it reached 100 for Intel. Okay, so as I said, what is Ilia useful? Why is Ilia useful is that it makes it independent of the architecture, the code independent of the architecture. And after it simplified data flow analysis, because you just have to do it once for everything, and you will see I'm going to show the code just after to data flow analysis in our language. That's it. So we have two additional commands which are use and def. So basically we know once we have translated the code, we call another function which is that function. And that function does what? It computes the data flow analysis, so it allows us to construct the data flow graphs we have shown a little bit before. So basically, depending on each instruction of the intermediate form, we know exactly which variable is used and which one is defined. So that allows us to say, okay, the source is used, so we recall its use into what we call a registry. So each block has a registry. So first we compute the intra-block data flow analysis, then inter-block data flow analysis, and finally inter-procedural data flow analysis. So this is how you do it on a couple of instructions. It is nothing magic, it's just about using the use and def commands, so that you can say, okay, this variable is used, this variable is defined, and automatically it will construct the data flow graph for you. Because for constructing a data flow graph, you just need diffuse chains, at least as long as you don't deal with alias analysis. So this kind of very simple code, you see just a couple of lines, then you can construct data flow graphs already. That's why the domain-specific language is really relevant, because, can you hear me? Okay. That's why it's really relevant, because just in a couple of lines you can do what you would do in hundreds of lines of C or even C++. That's what's the main motivation of designing that language. 10 minutes? A small demonstration after. Any question about what I just said? Yeah?
Why did you decide to actually write a whole language and not just a library for an existing
Just a library for?
For an existing language, like, I don't know, a library for OCaml or for Haskell or whatever.
Well, Haskell is a mathematical language, so I love Haskell. The concepts behind Haskell are excellent. However, I don't want to deal with monads to do data flow analysis, you know. And as for OCaml, the syntax of OCaml is great, but it doesn't allow us to do a post side effects. So if you have a match, you code in OCaml?
I know a little.
So basically, you cannot do everything we want in OCaml. Basically, this implementation of the domain-specific language can be done in OCaml. So the implementation of the DSL language itself can be done in a higher level language too. It's just that we want to have our own syntax and we want to define our syntax. And this is the best syntax you can have for doing data flow analysis and program transformation. So you take OCaml, okay.
It's not like OCaml, maybe a language like Ruby that allows you to pass blocks or stuff. Or
In Ruby, can you do switches on types?
no like
That's why you cannot use Ruby. So the only language I know that does this is OCaml, is ML. So the best language to write an interpreter of the RSE domain-specific language is OCaml. Well, in our case, we did a prototype in C because it's like that. For historical reason, we did it in C. But if I had to do it right now, I would do it in OCaml. And I'm going to finish by a small demonstration. Actually, I want to show you. It's not the whole thing I want to show you, but just the latest advance we have and how you can use RSE. I'm just going to run the program to show how it dumps graphs. So this is a very simple program that has a couple of functions and it makes use of free and malloc and everything. So this is called a call graph. So it's the graph between functions. This is a control flow graph, so you guys must be pretty familiar with it. So this is a control flow graph. So this is Spark code. I just took Spark code because it's complete and it's easy to do demonstration. So this is a control flow graph. And this is a control flow graph after transformation. So as I mentioned, you see you have the higher level intermediate instruction. So prolog, assign, IR, and stuff like that. And well, there are so many features in that program that I could pass like 3 more hours to just demonstrate it. But the whole code is public. We have a public SVN. Oh, we like right now we are reaching like a team of around 10 developers. So if you want to give a hand to us, if you want to join us, just come talk to me later, so we can arrange something. We have great developers. We have people that I just finished to develop the compatibility with the GDB protocol. So it means that now we will be capable to not only static analysis but dynamic analysis of a VMware node, of a box node, of a QEMU nodes and stuff. So we are entering the system somehow. Well, that's it. Thank you very much.